Okay, in this series of lectures, what we are going to discuss is materials testing. Say you have a structure, and that structure is bearing some load, and you want to know as a result of that bearing load what will be the deformation. Okay, for that you need to know some material property, and in order to know those material properties you need to do some testing. Okay, and one of the simplest and very important testing is the tension test. Okay, so this is what we're going to discuss. So what is this tension test, and what are the things we get to know through this tension test? This tension test, okay, first let me show the instrument with which the tension test is being performed. Right, so which is known as UTM machine. It's a short form for universal testing machine. Okay, so this is the schematic of that machine. Okay, and in this one, this is a movable crosshead, and this is an upper crosshead. Okay, a specimen will be in the form of a cylinder. Okay, a cylindrical rod that will be kept between the upper crosshead and movable crosshead, and by driving this screw we could move this movable crosshead up and down. Okay, and then simultaneously we will also measure, and we will keep the specimen over here, and when we move this crosshead, it will stretch. That specimen will get stretched, and while it stretch, we will also measure what is the load that particular specimen is bearing for that particular stretch. Okay, so from this we will get to know the relation between what is the stretch for an applied load, or what is the load for an applied stretch for a given stretch. So that's what we measure, and from this data we will get to know the property of this the material which we test. Okay, so that's UTM. That's a UTM machine, and that's a schematic sketch, and this is the actual machine. So here we will put the specimen, and this is the movable one. Okay, and it's with an automatic controller we'll be able to control, not an automatical controller. Here we have buttons. With these buttons we will be able to control the movement of this movable crosshead. Okay, so that's about this machine. Now let's see what are the things we could know from this. So from this we will be able to plot something called engineering stress versus engineering strain curve. So what is this engineering stress and engineering strain curve? So this S is called engineering stress, and P is the applied load, and A naught is the cross section area of that specimen, where naught represents the initial or the original cross section area. Okay, and this is also described as an average longitudinal stress. And why it's been called average is because in that cross-sectional area, okay, we are interested to know the intensity of the force which we have applied. Okay, and it's not necessary that the intensity, which means the force per each infinitesimal piece of area, okay, that intensity is not necessary to be uniform, but what we do is we assume it's being uniform, or even if it's non-uniform, we are getting an average value by dividing the total load by the whole area, okay. So therefore it's been called average longitudinal stress. And for engineering stress, what we are doing is we are considering the initial area or original area, okay. So that's engineering stress. And let's see what is engineering strain. So the engineering strain is denoted as small e, which is the change in length, okay. So this is the change in length per original length, which means initial length, which is also known as gauge length, okay. And this is the final length, the current length, okay, and initial length. So that's the change in length divided by original length, okay. I think this L naught is missing here. Anyway, so that is being called engineering strain. And if you notice, this engineering strain is also an average linear strain, okay. So why it's being called average linear strain? Because say the specimen is with a length of L naught, okay. In that specimen with L naught length, we could divide that specimen into many number of infinitesimal pieces, and each infinitesimal pieces will get stretched, and it's not necessary that it will get stretched uniformly, okay. But if we average the strain of each infinitesimal piece, then we will get some average strain value, and that average strain value is this one, okay. And therefore it's been called average linear strain. Fine. So this is an engineering strain, and the S is engineering stress, okay. And from the UTM machine, let's see whether we will be able to identify this E and S. Let's see this one first. So this is the load, okay, that we could measure, and this is the cross section area, the initial cross section area that we could measure. So before we put it into the UTM machine, we could measure the cross section area. So yes, and we could know this P, and we could know this A. Now therefore we could know this S for different loading, okay. And at the same time we could also know this E for each corresponding S, or we could know S for each corresponding E. How do we measure E? So it's a change in length per the original length, right? So the change in length, if you see this, yeah, so this is a screw, right? And we control this rotation of the screw, and therefore we could control the movement of this head. So somehow we could measure what is the distance between here and here, which means we could know what is the change in distance, which is the displacement, okay. So therefore we do know L, okay, and we could measure the initial length L naught, and therefore we could measure what is E. Now what we do is, once we know all these things for different E and different S, we will plot it, and if we plot for a metal, we will get somewhat like this. Okay, and this is known as engineering stress strain curve. Fine. Now from this engineering stress strain curve, what are the things we could know? We could know various things, but before that, we will see one more thing. So if you see, it's totally not linear as Hook mentioned. Okay, so it's linear for certain range, and after that it becomes non-linear. Okay, and at this point what will happen? At this point it will break, the specimen will break. Okay, okay, now if I apply the load somewhere in between, I mean say up to here, and then say I'm unloading, what will happen? So if we observe it, this is what will happen. Okay, so if I load it, say I go up to point B, and then if I unload it, I will not go in this way, okay, but I will go in this line, along this line. Okay, so this is the loading path and this is the unloading path, and in case if I load it up to here and unload it, this will be my unloading curve. And once again if I load it, I will go along this line, and not that I will be going over here and come like this. Okay, so that's a behavior of the material. And so once I load it, okay, for example, if I load up to here and if I unload it, I will come back to this origin. But at the same time, if I load it up to point A or point B, I cannot come to origin. So there is a permanent deformation. Okay, and that permanent deformation is known as plastic deformation. Okay, which is not completely recoverable. Okay, but at the same time certain amount has been recovered, and that is known as elastic recoverable strain. Okay, fine. So okay, with this curve, what are the things we could measure? So one thing is the tensile strength. So what is this tensile strength? Once again we will go to this picture. Okay, so in this picture we refer the stress at this point. So if you see, the stresses keep on increasing, and once it reaches here, the stress starts getting decreased. Okay, so up to this point it's increasing, and after that it's decreasing, and this is the maximum bearable stress, maximum bearable engineering stress of the material, and that maximum bearable stress is known as tensile strength. Okay, so if you want to break the material, we need to apply at least this much of stress. Okay, and how it's been denoted? So it's been denoted as SU to represent the ultimate tensile strength, which is equal to the P max divided by original cross section area. Okay, fine. What else we could measure? So we could measure yielding. Okay, so what is yielding? Yielding is a point where the permanent deformation will occur. Okay, For example, if I apply the load up to here and if I unload it, it will go back to the origin, but at the same time if I upload it somewhere up to here and unload it, it will come back here but not to the origin. Okay, so there is a permanent deformation. So the yield point is a point where it begins to have a permanent or plastic deformation. So that's what the yield point or the yield strength means. Okay, how to identify the yield point? In order to identify the yield point, we may have to load and unload to every incremental or every possible conventional strain, but that's very difficult. Therefore, what we do is we just use this stress strain curve, and this stress strain curve, what we do is we'll take some offset, okay, offset of 0.2% strain, okay, and then from that point we'll draw a straight line, and that straight line is parallel to this line, the initial slope of this curve, and that will intersect at some point, right? And that point is called offset yield strength and or yield point. Okay, so that's one way of identifying the yield limit. Okay, and for some other material, people use another method. Another method is like they will choose a point where the strain is 0.5%, and from that point they will draw a vertical line, okay, and when they draw a vertical line, that will intersect this stress strain curve, and they will consider that point as the yield point. Okay, so for certain materials they will consider the vertical line, and for certain other materials they consider this offset parallel line. Okay, so that's how we can identify the yield strength. So the yield strength is the limit up to which or beyond which the material will have a permanent deformation. Okay, what else we could measure? So we have measured tensile strength and yielding. Okay, and once again so tensile strength is defined as denoted as S naught, which is equal to P at that offset load and divided by A naught. Okay, see, so 0.5% is used for some soft materials where the stress strain curve will not have a linear portion. Okay, so like Hooke's law, there will be a region where stress is proportional to strain, but for some materials like soft copper or grey cast iron, we can't have such a straight line, and therefore we use this method. Okay, so what is the other thing? The other thing is the measures of ductility. So what is ductility? It's a quality of the material which is possible to deform it, okay, so that we could make it to some shape before it gets fractured, okay, before it gets break. Okay, how much I could deform it before it gets break. So that's what the measure of ductility. And why do we need it? So that we'll get to know whether I could change the shape of that material from one form to another. Okay, so for example in the punching process, or some metal forming process, it will go through a large deformation, but whether that material could withstand or not depends on the ductility. If the material's ductility is more, then yes, it is we can use it for forming process, otherwise we cannot do it. Okay, how to measure this ductility? So the ductility is being measured using this formula EF, which is equal to LF minus L0. What is LF? It is L0 is the initial gauge length, LF is the gauge length at fracture. Okay, so the EF is the engineering strain at fracture. So in this picture, if we see, what is it? It is this particular strain. So this particular strain value is one measure. So if this is large, then I could understand that it will deform plastically more. Okay, because here we have the yield limit, and now up to here I could deform it. Okay, so which means I could deform the material plastic. There will be a large plastic deformation before it fails. Okay, which means it's more ductile. If it's going to fail somewhere at this point, then it's very less ductile and I cannot use it to some forming process. Okay, so this is one measure. So if this strain is more, then it's more ductile, otherwise it's less ductile. Okay, but if you notice, we could measure using this another equation. What is this? So the Q is something called reduction of area. Okay, so what is this reduction of area? This A0 is the initial cross section. Okay, and AF is the final cross section. Okay, so A0 minus AF by A0 is showing how much kind of what is the ratio of the change in the cross section. Okay, so that is also a good measure of ductility. So we could use either this one or this one. Okay, and then if you see, they have shown the relation between this E0 and Q. Okay, so what is it? Or yeah, at yield point. Okay, so what is this E0 and Q? In order to identify the relation between E and Q, what we do is, during plastic deformation, okay, there won't be any change in volume. It's a volume preserving deformation. So that's an assumption. That assumption is obtained based on the experimental evidence. From the experimental evidence, we have observed that there isn't any volume change. Therefore, what we could do is, we could assume the volume of the specimen initially, which is cross section area A0 into L0, which is equal to the current area, cross section area into the current gauge length. Okay, okay, so now if we use this relation, from this I can say L by L0 is equal to A0 by A. But from this relation, I could say A naught by A, which is equal to 1 by 1 minus Q. Okay, so now if L minus L naught by L naught, which is equal to, okay, once again from this relation, A naught by A minus 1, that we could do. How? Simple. Divide this thing by L naught, which will provide us L by L naught minus L naught by L naught, where L naught by L naught becomes 1. So L by L naught becomes A naught by A. So A naught by A minus 1, which is equal to 1 by 1 minus Q, which comes from here, minus 1, which is equal to Q by 1 minus Q. Okay, so that's a relation. So that's a relation between the engineering strain and reduction in cross-section area. Okay, fine. So that's one thing. And yeah, so here there are other measures that what is the strain at the ultimate loading. So when the load reaches the maximum, at that time what is the strain? Maybe people consider that as one of the measure. Okay, so those are some measures for ductility. And another one is Young's modulus, or modulus of elasticity. So that modulus of elasticity, I mean, that's well known, which is nothing but the slope of this elastic region. Okay, so slope of the elastic region, and that is being okay, so that's actually the stress by strain. I mean, that's just the slope. And if we notice, for some materials, I mean, this table for some materials, the Young's modulus has been given for various temperature. And if you notice, for an increasing temperature, the Young's modulus, or modulus of elasticity, is decreasing. Okay, so that is one thing which is noticeable. Okay, so now we'll see a problem. So in this problem, a 13 mm diameter tensile specimen has a 50 mm gauge length. Okay, so now from the 0.2% offset, so yield point has been identified, which is this one. Okay, and the maximum load, which is P max, okay, which has been observed from the stress strain curve. And the fracture occurs at this load. Now the diameter after fracture is 8 mm, and the gauge length at fracture is 65 mm. Okay, so it's after fracture. And have they mentioned the initial fracture? No, they haven't. Okay, so initial diameter, they haven't given the initial diameter, but initial gauge length has been given, which is 50 mm. Okay, calculate the standard properties of the material from the tension test. Okay, so one thing we could measure is, well, initially with the diameter they have measured what is the original cross-section area and what is the final cross-section area. Okay, So one thing we could measure is okay, from this data we could measure what is the ultimate tensile strength. Okay, so ultimate tensile strength is P max by A naught, and we know what is the P max. Okay, so from this we have obtained what is SU. And then yield strength. For yield strength we need to use this as P divided by this cross section area. So that's how we have obtained this one. And then the breaking stress or fracture stress, which is denoted as SF, and for this PF, which we could obtain from this data. Okay, fine. Now what else we could measure? EF. Okay, because that's from that we could understand what is the ductility. Okay, so LF is 65 and L naught is 50, and if we put these values into this equation, we get 30%. Okay, so it's a very large elongation, which means it's more ductile. Okay, and I don't think we could measure the Young's modulus, but that's okay. But one more thing, if you notice, we could also measure the reduction of area. Okay, so I think yeah, the initial diameter has been given. Okay, which is 62%, right? And yeah, so reduction of area, the formula is A naught minus AF by A naught, and if we plug in the numbers, we'll get this is 62%, and if you notice, this value is different from this value. Okay. Okay, so now the question is, if this E is equal to 207 GPa, then the question is, what is the elastic recoverable strain at maximum load, which means I have reached up to maximum load and then I start unloading. Okay, when I start unloading, that will be the maximum recoverable strain. Okay, so which is ultimate engineering stress divided by Young's modulus, which will give us this as the maximum recoverable elastic strain. Okay, and since we know, okay, what is this, if the elongation of maximum load is 22%, okay, what is the plastic strain at maximum load? Okay, that's simple. So this is the total strain. Okay, in that total strain, this is the amount which we could recover. Okay, the remaining thing is the plastic strain. Okay, so we just have to subtract this to this, which is 0.22 minus 0.003, which is 0.2170. Okay, so we could measure various properties just with the stress strain curve. Okay, in the following video we will see some other properties using the same stress strain curve. Okay, thank you.